Hello everyone, welcome back to another episode of Geoscience Explorer. Igneous rocks compose the majority of Earth's crust. They are born from intense heat and create stunning sights like volcanoes. They also form deep beneath the surface, where pressure and time work together to build massive structures of solid rock. Many of the world's mountains and ocean floors are made of these fiery origins. Even the minerals inside igneous rocks can reveal the temperature and speed at which they formed. Their presence shows how active and restless our planet truly is. Every igneous rock carries a story of fire, transformation, and the powerful forces shaping Earth. Igneous rocks are rocks that form when molten material cools and solidifies. Molten material consists of rock that has been heated enough to melt into a liquid-like state. That molten material can be magma, molten rock beneath our surface, or lava, molten rock that erupts onto the surface. So magma and lava are different, but when magma or lava cools, it crystallizes into solid rock. As the temperature drops, the particles slow down and start locking together, creating solid mineral crystals. Because they form from melted material, igneous rocks are often called the parent rocks of the rock cycle. For more info on the rock cycle, please check out this video. Nevertheless, sedimentary and metamorphic rocks can ultimately be traced back to these fiery beginnings. To understand how igneous rocks form, we need to imagine Earth not as an inactive, solid world, but as a restless planet with heat constantly moving beneath its surface. Far below us lies the mantle, a layer so hot that rock doesn't behave like the rigid stone we see on the surface. Instead, it becomes a thick, glowing, putty-like material called magma. Magma can flow like a liquid, but it isn't fully liquid. It's a mixture of solid crystals, melted rock, and trapped gases all blended together. Because of this, there are no giant oceans of liquid rock directly beneath our feet. That wouldn't even make sense. A fully liquid layer would be less dense than the solid rock, and so it would rise towards the surface instead of staying deep underground. Most of the mantle is solid, but capable of very slow movement, and only in special places does enough melting occur for magma to form. And that magma, whether it cools quietly underground or erupts at the surface, is the beginning of every igneous rock story. As magma rises, it doesn't always reach the surface. Sometimes it gets trapped miles underground in huge pockets or cracks in the crust. When that happens, the magma begins to cool very slowly, sometimes over thousands or even millions of years, and the temperature drops. A process called crystallization begins. During crystallization, the atoms inside the magma arrange themselves into solid, orderly mineral crystals. Because this cooling takes so long, the crystals have plenty of time to grow large and visible. This type of igneous rock is called intrusive or plutonic rock. Granite is a perfect example. Its big, sparkly mineral grains, like quartz and feldspar, are a clue that it formed deep underground, where cooling was slow and steady. But magma doesn't always stay hidden. Sometimes pressure builds, cracks open, and the molten rock bursts out at the surface. The moment magma reaches the outside world, it's given a new name, lava. Lava cools much faster because it's suddenly exposed to air or water that is much cooler than the molten rock. Rapid cooling means the minerals barely have time to grow crystals at all. The result is extrusive or volcanic igneous rock. Basalt is the most common example, fine grained, dark, and formed from lava that cooled quickly. In extreme cases where cooling happens almost instantly, like when lava hits cold ocean water, you can even get volcanic glass, such as obsidian, which has no visible crystals at all. When magma begins to cool, the story of an igneous rock shifts from fiery motion to the slow, patient work of forming texture. And in the world of igneous rocks, texture means one thing above all else: how the crystals form during cooling. Each texture captures a moment in that cooling journey, like a photograph frozen in stone. Deep underground, where everything happens slowly, minerals have all the time they need to grow. They spread outward, locking together into big, easily visible crystals. This is the phaneritic texture, coarse-grained rocks like granite, where every crystal is a clear record of a long, steady cooling process. But if the magma reaches the surface and cools quickly, the story changes. The minerals don't have much time to grow, so they form into tiny crystals that are small to see. This creates the aphanitic texture, found in rocks like basalt. It's the texture of speed, lava cooling so fast that its crystals barely have a chance to form. Sometimes, though, magma begins cooling underground, forming a few large crystals and then erupts to finish cooling at the surface. This creates a mixture of crystal sizes. The big crystals, called phenocrysts, sit inside a fine-grained background. This is the porphyritic texture, a texture that tells a two-part story: slow cooling first, then sudden cooling later. But cooling can even be more dramatic. If the lava cools almost instantly, perhaps blasted into the air or quenched in water, crystals don't have the chance to form at all. The magma freezes into a solid mass of unordered atoms, creating the glassy texture. Obsidian is the perfect example: dark, shiny, and smooth, as if the rock skipped the crystal stage entirely. Explosive eruptions can also trap gas in the lava. When that gas escapes during cooling, it leaves behind holes called vesicles. Rocks like pumice and scoria have this vesicular texture, full of tiny pockets that make them look light and frothy. These rocks are reminders that even gases shape the final form of molten rock. And in the most violent eruptions, the magma is torn apart. Ash, fragments of molten rock, and broken crystals are blasted into the air and settle as a chaotic layer of debris. When these fragments fuse together, they create the pyroclastic texture, a texture born from destruction, telling stories of explosive power and volcanic fury. Together, these six textures, phaneritic, aphanitic, porphyritic, glassy, vesicular, and pyroclastic, are the final signatures of magma's journey. Each one captures a unique set of conditions: slow cooling, fast cooling, sudden eruptions, trapped gases, or explosive fragmentation. And when geologists view these textures, they begin to understand the molten story that occurs on our planet. To understand why igneous rocks look the way they do, why some are dark and heavy while others are light, we need to understand the minerals they are made of. For an in-depth understanding of minerals, check out this video. We turn to one of the most important tools in geology, Bowen's reaction series. It's more than a chart. It's a map of how minerals form as magma cools, revealing which minerals grow first and which appear later, and why certain minerals always seem to appear together. Imagine a chamber of magma slowly cooling deep inside the earth. At the very top of Bowen's series, the minerals that form first are the ones that can tolerate the highest temperatures. These early forming minerals, olivine, pyroxene, and calcium-rich plagioclase feldspar, or anorthite, create dark, dense igneous rocks known as mafic rocks. Basalt and gabbro are rich in these minerals, and their composition tells us how they crystallize from hot, magnesium and iron-rich lavas or magmas. As the temperature drops, the magma's chemistry begins to change. The minerals that used to be stable start to disappear, and new minerals take their place. This is the reaction part of Bowen's reaction series. Early crystals react with the remaining melt, transforming into entirely new minerals. Olivine gives way to pyroxene, pyroxene shifts to amphibole, and amphibole eventually becomes biotite. This pathway is called the discontinuous branch, where each mineral has a distinct, separate structure. Meanwhile, on the other side, the continuous branch shows how plagioclase feldspar changes gradually from calcium-rich to sodium-rich as the magma cools. Instead of forming totally new minerals, the feldspar simply adjusts its chemistry step by step. It's the quiet, steady evolution of a mineral adapting to cooler conditions. Eventually, near the bottom of Bowen's series, the magma has cooled enough for the low-temperature minerals to form: muscovite, potassium feldspar, and quartz. These minerals create felsic rocks, like rhyolite and granite, which are light in color and rich in silica. By the time quartz forms, the magma is nearing the end of its journey, solidifying into rock that once cooled slowly and peacefully in Earth's crust. So, the mineral composition of an igneous rock is not random. It's a timeline. Mafic rocks capture the earliest stages of cooling. Intermediate rocks like andesite and diorite record the middle of the sequence. and felsic rocks preserve the final, coolest moments of crystallization. Igneous rocks stand as solid proof that our planet is never truly still. Some begin in places we'll never see, and yet they end up in our hands, on our mountains, and beneath our feet. As we explore these rocks, we're not just identifying minerals or naming textures. We're uncovering the history of how Earth builds and rebuilds itself. And as long as Earth continues to churn and shift from within, new igneous rocks will form, carrying the next chapter of Earth's story. Thanks for watching. Stay tuned for more rock-solid facts and stellar vibes.